Alright, hello Trig or Calc or whatever this class is now. Today we are looking at continuity. So continuity is basically just a fancy way of saying whether a function is continuous. And our function is continuous if basically three things are happening. So it's continuous at a point if that point exists. Kind of makes sense. If the limit at that point exists, which again is not necessarily the same thing as that point existing, the limit just means are we approaching the same thing from the left as we are from the right. So the point has to exist, the limit has to exist. And the last thing is those two things have to be the same thing. So the point and the limit, they both need to exist and they need to be the same thing. And in general, it's probably easier to picture when a function isn't continuous than when it is. Because all of our nice linear graphs, all of our nice parabolas, those are all continuous everywhere. The points we're really interested in are the points where it's not doing that. So if it's not doing that, there are a couple different things that could be happening. So our function isn't continuous everywhere if, first thing could be an asymptote. So if we've got something like this, and then something like this, where we've got this point, where it's not continuous, then it's not continuous there. It's continuous everywhere else, but not at that particular point. The other thing, well, one of the other things that could happen is we could have a hole there. So maybe our line is chugging along just nicely until we get to this point where there's not a point, and then it just keeps on going. So the limit exists, but the point doesn't. So in order to be continuous, it has to have those three things. So the point and the limit both have to exist, and they have to be the same thing. Here, the point doesn't exist. Here, a point doesn't exist. Also, the limit doesn't exist. So the other thing that could be going on is if you've got something going on that's piecewise. So if I've got something where I've got this, and then I jump down here, and let me make that hole empty. There we go. And then we continue off from here. So this point exists. Technically, the limit also exists because we're approaching the same thing from this direction as we are from this direction. So the point exists, the limit exists, but this would be an example of where those two things aren't the same thing. So the point has to exist, the limit has to exist, and they have to be the same thing. Now, again, this is continuous everywhere else, just not at this point. So it's continuous over here. This is still continuous over here, just not at that particular point. So what we're doing with this is we're just basically figuring out where a function is continuous. So if I have, say, this function, we want to know where is it continuous? Where is it not continuous? So if we have something like this and we didn't want to, say, just graph it, we're going to go ahead and we're going to factor the bottom. Because in general, things like asymptotes and holes are coming from a couple of different things. If we've got fractions, they're probably coming from where the bottom of the fraction is 0. So if we're looking for where x squared plus 4 equals 0, and we didn't want to just graph it, we're going to subtract that 4. And we got x squared equals 4. So either positive 2 or negative 2 are where something is going on. Or the other thing you could do is you could factor the bottom into an x plus 2 and an x minus 2, and that's going to be useful in a moment. So those are the 2 points where we don't have a continuous function because we don't have a point there. So in order to be continuous, the point has to exist. Here, the point just plain doesn't exist, so we know it's not continuous there. So there are a couple different ways that you could say where it's not or where it is continuous and where it's not continuous. Probably the simplest thing to do is to just say it's continuous everywhere except positive and negative 2. Now, the other thing you can do with this is, since we factored the bottom into an x plus 2 and an x minus 2, if we want a similar function that would be continuous in more places, we're going to go ahead and cross off that x plus 2 and that x plus 2. So we got a 1 over that x minus 2, because if there's nothing left on top, it's a 1. So this is a function that is almost exactly the same, but is continuous in everywhere except positive 2 rather than both positive and negative 2. So if you see something in the homework that says we want to extend f to a function that is continuous on a larger domain, that's what we're looking for. This is your function that's continuous on a larger domain. Not everywhere, but in a larger domain than the other one was. So if you see that phrasing, that's what we're looking for. We're looking for a function that's the same everywhere except that point. Now, also, feel free to go through and graph those. I went ahead and, yeah, you definitely can't see that, so I'm not even going to show you that. I'm assuming at this point, oh, hey, almost got the glare to where it wasn't. Maybe if I make the screen less bright, that kind of helped. Okay, so you can kind of see what's going on there now. So we've got, oops, the top function is the one that we started with first of all. That's the one in red, so it's continuous everywhere except at this point, which it's not going to let me click on. Come on. Yeah, there we go. So it's continuous everywhere except at that negative 2 where it's undefined that you probably can't see. Yeah, no. I'm going to assume at this point that you know how to use Desmos and you can find that on your own. Yay. So it's continuous everywhere except that point, and then the blue function is the second one where it's the same as our first one except at that particular point. There we go. So, sorry that Desmos thing didn't work. If this keeps going on long enough, I'll have to find some way to screen share what I've got on my screen up there. But, I mean, you can use Desmos. I know you can use Desmos. So, that one's continuous everywhere except there, and that was our function that we extended to be continuous on a larger domain. Fancy words for just get rid of the thing that's going to cancel out. Okay. What about this one? So if you happen to remember that square root functions in general are going to look something like this. And this is going to start off at negative 1, 0, because in general what's giving us things with square roots where we don't have points is where the inside of that square root would be a negative. So anything smaller than negative 1 here for x, so like negative 2 is going to give us a negative 1 inside of our square root. So our graph actually starts being a thing here. So if we want where that function is continuous, then we're going to be continuous everywhere from that negative 1 going off to positive infinity, or if you want to call that x is greater than or equal to negative 1, I don't particularly care whether you're using that notation or that notation, same thing. And this one, we don't really have a way that we can extend that to a function where it's similar but has a different domain, so sometimes that's going to work, sometimes that's not, so if it doesn't, don't sweat it. The last thing that could be going on is if we got something piecewise. So if we got something piecewise, what we're really interested in is the points where those are meeting. Because 2x, that's just a line. That's going to be continuous everywhere on its own. X plus 1 is just a line. That's going to be continuous. X squared is just a parabola. All of those are continuous on their own. So we're really just interested in the parts where those piecewise functions are either meeting or they're not. Whether we're going to get something like this where they're meeting and then heading off in different directions, or whether we've got something like this where they just don't meet at all. So we're really just interested in those things. So we're really interested in what's going on at 2 points. We're interested in what's going on at 1 where this function is meeting this function, and what's going on at 3 where this function is meeting this function. We really don't care about any of our other points. So if you don't want to graph this, the quickest way to find out if they're meeting is to just plug that 1 into both this and this. 2 times 1 is 2. 1 plus 1 is 2. So these two, even though they're two different pieces, they're both meeting up at 1, 2. So that's still continuous because the point exists, the limit exists, it's approaching the same thing, and the point is the same as the limit. So even though we got a piecewise function, that part's still meeting up, that's still continuous. Now if we take 3 and we plug that into both this one and this one, I'm going to use a different color. So if we plug 3 into both here and here, because those are the functions that are ending at 3, 3 plus 1 is 4. 3 squared is 9, which is not 4. 9 is not 4. So, yeah, you're in trig and you're learning that 9 is not 4. Okay, so 9 is not 4, so that means we're not continuous there. So we're not continuous, or we're discontinuous at x equals 3. So again, you could either just say that that is where we're not continuous, or the other thing you could do is we could say we are continuous everywhere from negative infinity to 3, and then also from 3 going off to positive infinity. So if you've really just got 1 or 2 points where it's not continuous, this is probably the easier way to do this. Where this becomes useful is if you've got like 5 or 6 or 7 different points where it's not continuous. None of these are going to be that obnoxious, so this is fine. If you really like interval notation, you can also do that. Same thing. Alright, so that is pretty much it for continuity. I'm going to assume by this point you've already skipped the rest of the video and gone ahead and gotten started on the homework, and you're probably only coming back to this if there's something you got stuck on. So if there's something you got stuck on, feel free to throw something in the comments or just email me, because there's only one of you, so there's not really any point to putting something in the comments for other people to see. So feel free to email me if you have questions. Homework is in the description below, and this is McDuff. Okay, that's good.